Okay, welcome back. We'll continue. Today, in this first unit, we are going to finish up our study of kinematics of motion. Okay? If you recall, in the unit that just ended, we looked at this idea of the polar decomposition, right? We saw how the deformation gradient can be decomposed into, in general, into a rotation and stretch. And we looked at all the implications that this had, right? And we saw that there were actually two kinds of polar decompositions, okay? There's just one thing I need to finish up with regard to that, which is that we introduced a bunch of new tensors, and we treated them mainly in direct notation. What I'm going to do in the first few minutes now is to write out coordinate notation for those tensors, okay? So let's start there. Let's start by recalling the polar decompositions. Okay, I say polar decompositions in plural simply because we know that there are two of them, right? So let's first look at the right polar decomposition. Let's recall the right polar decomposition. All right, this is F, and remember that F is just partial of the motion with respect to reference position, and the right polar decomposition says that this is Ru, where, as we made clear, R belongs to SO3, right? We also saw in response to a question that the determinant of R equals 1, because in general SO3 admits determinants of plus or minus 1. We also saw that U belongs to the space of symmetric tensors in 3 dimensions, and in particular the space of symmetric tensors with positive determinant. Okay, so R is the rotation and U is the stretch. We saw as well that that this other tensor that we'd introduced a little before the polar decomposition, the right Cauchy-Green tensor, if you just substitute for the polar decomposition in this equation, leads us to conclude that C equals U square. Okay, using all the properties we've written above for U. Now, what I want to do is to first write out C using coordinate notation. Okay, so in coordinate notation, I'm going to write C here, and I'm not going to put indices on it just yet. I want these indices to come out from our little calculation above here. Okay, so C is F transpose F, and now writing out the indices for F, remember how this works out. You may observe that I've already skipped a step on the right-hand side. I've directly written F transpose in terms of the components of F, right? And the fact that it's a transpose is revealed by the fact that it is the index little I that's being contracted out. Okay? So this, now when you carry out this contraction, the free indices that are left are capital I, capital J. Okay? That is the manner in which C is written in coordinate notation. Observe that it uses uppercase indices. This should not be a big surprise because remember that C acts upon vectors defined in omega naught. Okay? So, to see why this particular way of writing the coordinates of C makes sense, let's recall what the action of C is. Okay? Remember that if we have a vector, say y minus x, belonging to omega naught, the reference configuration, and this simply means that we have points y and x here, right? And so then the vector y minus x is that vector. Doesn't look terribly like a vector because I drew it a little wavy, but it's meant to be a vector. Okay? All right, so if y minus x belongs to omega naught, we know that C acts on y minus x. Okay? And then you can dot it on the left also with y minus x. Okay? And then this gives us the stretched vector right under the deformation. Okay? And we've been writing this as in omega sub t. We've been calling the new position of those points little y and little x, right? Okay? And we saw that this is essentially y minus x, little y minus little x, Euclidean norm square. Okay? So now if we ask ourselves, well, how would the coordinates have to work out? It should be clear that C had better have uppercase indices, right? The fact that it has uppercase indices, let's say ij, as we derived on the previous slide, allows us to make sense of the above formula. Sorry, there should be j's here. Well, right? It allows us to make sense of the above formula in the following way. Okay? Y minus x being a vector in omega naught, of course, admits uppercase indices. So C also had better have uppercase indices. Okay? For all of this to work out. Okay. Now, likewise, what we see is that what we observe, since we know that U equals U transpose and U square equals C. Those two relations imply that U had also better have uppercase indices. Okay? What this implies then is that we would write U as U capital I capital J EI tensor EJ. Okay? And it's those two conditions that I've written here, U equals U transpose and U square equals C, that are important here because those conditions are what imply that now if I write C maybe KL, we see that this thing works out very well if we give U uppercase indices. Okay? So U also has uppercase indices. And we also saw that actually U is simply the it's simply the Euclidean norm of the stretch of a vector stretched, right? Without the square. So again, the fact that it acts upon vectors in right? So the very fact that U acts on vectors in omega naught and leaves us with the norm, the Euclidean norm of this vector stretched, okay, is what says that it too should have uppercase indices, okay? All right. Okay. What about R now? Okay. Now remember that this is how things have to work out, right? Fii has to be equal to R, some indices, U, let's say Ji. Okay? And just by inspection here, we know that R has to have indices little I, little j. Okay? So those are the indices of R. Like F, R is what we call a two-point tensor because one of its indices lives in the reference configuration and the other in the current configuration. All right? Okay. So these were the results for the right polar decomposition. Let's now see very quickly how this works out for the left polar decomposition. I'm just going to write out these results briefly without going into the detail that we went into for the right polar decomposition. Okay? For the left polar decomposition, okay, and recall that that left polar decomposition is F equals VR. Okay? And remember that we also showed last time, or we at least wrote out last time, that there is the left Cauchy-Green stretching tensor, right? B, which is F transpose. When we make the substitution of the left polar decomposition in this last equation I've written, what we observe is that B equals B square. Okay? Now, coordinate notation. B, no indices because I want to fill them in. It's F, I, F, J, I. Once again, I've skipped a step by writing the components of F transpose directly in terms of the components of F. And we see how that product is carried out. It is the uppercase index I that is being contracted out. Okay? And this, of course, leaves us with three indices, little I, little j, which then are the indices of B. Now, if you recall that B as well as B inverse act on vectors in the current configuration, those indices make sense. Okay? Proceeding as we did for the right polar decomposition and recalling that V equals V transpose, as well as, and this is all since V equals V transpose, as well as the fact that V square equals B, right? What this does is it implies that V can also be written as V little I, little j, EI tensor EJ. Okay? As for B, so for V, the indices are lowercase ones. Okay? And the arguments here, I haven't gone into them in detail, but we essentially saw how it worked out for the right polar decomposition. The same arguments work out here, except that everything ends up as lowercase indices. Okay? And we see now that all of this does indeed work out consistently, because now if we go back and write the deformation gradient in terms of the left polar decomposition, we observe that things do indeed work out. Recall that R has indices lower and upper, right? Okay, so everything works out. Okay, so these are the this is how we write our newly introduced tensors around the polar decomposition in terms of their coordinate notation.